All right, so picking up where we just left off, we were talking about the sum and difference rule. The sum and difference rule lets us do things like find the derivative of this function really nice and easy. First thing we're going to do is break up that function into three different smaller derivatives. We're going to say we want the derivative of x cubed minus 4x plus 2 by rule 4. This is going to be equal to d dx of x cubed minus d dx of 4x plus d dx of 2. Now, by rule 3, we're going to pull out this 4 here. Now, by the power rule, actually, let's go with the constant rule first. The constant rule is going to send this to 0, right? So we're going to have d dx of x cubed minus 4 d dx of x plus 0. Everybody agree? Now, by the power rule, so that's rule 2, we're going to have 3 times x to the 3 minus 1 minus 4 times 1 times x to the 1 minus 1 which is equal to 3x to the second minus 4x to the 0th power or 3x squared minus 4.
Can you explain the power rule 2, how you do not rotate?
So coming back to the power rule over here, all it really says is that you're going to bring your power down as a constant. And then you're going to come over and say, all right, raise x to 1 less than that previous power.
Okay.
Cool?
Yeah, so the 3 minus 1 makes sense, but how did you do the 1 minus 1?
X
Oh.
is just
okay.
x to the first.
Okay.
So what would have been an arduous pain in the ass to figure out with the limit definition, using all of our rules, it's actually pretty quick and easy compared to what it would have been, right? And could you imagine having to do this with that limit definition? We'd be here all day and all night. Now, coming over here, we want to find the slope of the tangent line at the point 1, -1. So first, let's make sure that that's a point even on our graph. Plug in 1, you get 1 cubed, that's 1, minus 4 times 1, so that's 1 minus 4, so we have -3, plus 2, it's going to be -1. So 1, -1 is a point on our graph. So now, since f prime of x, our derivative, is equal to 3x squared minus 4, f prime at 1 is going to be equal to 3 at 1 squared minus 4, which is going to be equal to -1. It happens to be a fluke that this occurs, but this is the same as what your function was. It's just a freak of nature. There's a function that does that, but it's not this one. So what we just found was, given this function, this is the graph of our function, the slope of the tangent line right here is equal to -1. Now let's find that line. Let's find the equation of this line. Okay, let me actually. So we know our slope is -1, and we know xy is equal to 1, -1. To find this tangent line, we're going to use point slope form, right? So y minus -1 is equal to -1 times x minus 1 adding -1 to both sides. Now distributing this -1 all the way through. We get that the equation of our tangent line is equal to -x. Yeah, that's what I was trying to write. And if we look at this, it's actually kind of obvious, isn't it? Where that goes to the origin, right? So this has to be the line -x. So what we just found was the derivative of our function. Then we said, all right, we want the slope of our tangent line, or of the line tangent to our function, at the point 1, -1. So we want the slope of this line. So plug in 1 into our derivative. That gives us the slope of our tangent line is -1. And then we used point slope form to find the equation of that line. I'm going to go through this particular problem over and over and over and over again. And the reason why is because this is one of the most important parts of this class. Because it combines a lot of different things all at once. So let's say we wanted to find the equation of the tangent line to this function at this point. Step 1, what are we going to do? Don't everybody say it at once.
Prime.
Step 2, what are we going to do?
try and simplify the power or the rules?
Yeah, we can first start by simplifying, absolutely. In this case, there's nothing to simplify, right? So that's convenient for us. Step 3, we're gonna get a tissue to wipe up our tears. Step 4, we're gonna apply the derivative, right? We're gonna say, all right, well, since we're adding all of these together, yeah, the sum and difference rule. Then after that, constant rule, constant rule, constant rule. Then after that, power rule, power rule, power rule. Then we're gonna have the slope of our tangent line, or the derivative of our equation, I should say. Then we're gonna say, all right, first we need to make sure this is a point on our graph, or -1, 3, does it give us -3/2? If it does, now that we have the derivative, throw -1 to that derivative, and that's gonna tell us the slope of the tangent line to this function at this point. Then we're gonna use this point in point slope form, just like what we did up here. So find the derivative. Check to make sure that point is on your graph. If it is, then plug it into your derivative. Plug that x into your derivative. That's the slope of your tangent line. Then use that point and that slope in point slope form and reduce it down to slope intercept form. Cool.
What do you mean check to see if it's on your graph?
Because what if I gave you a point -110? It's not a solution to this.
Oh, okay,
That's what I meant.
okay.
We just have to make sure that this actually is a solution. Which, if we look at it, we've got 1 here, -1/2 here, -3 here, 2 here. So it looks like it might be. It is. So once we find the derivative of this thing, we're gonna find the slope, that happens to be 9. Then use slope intercept. Point slope. The derivative of that function is going to be -2 times x cubed plus 9x squared minus 2. After we've checked that that point is a solution of our function, we're going to plug in -1 and get that the slope of our tangent line is equal to 9. We're going to say, all right, cool, point slope form. And reduce it down to slope intercept form. Is everybody okay with this idea? This happens to be one of every calculus class's or every calculus instructor's favorite type of problems. Like, we all love this problem and giving it to our students because it does like half the class in one problem. Yeah, I can make as obtuse of a problem as I want and it have almost the entire class in it. So we love the tangent line problem. That's one of the reasons why I keep harping on it. It's useful. It's going to show up in the business world, depending upon what you do. Shows up literally everywhere. In fact, here is one example, modeling revenues. When talking about revenues, one thing we might want to know is the rate at which a revenue changes with time, or profit, or costs. And whenever you take the derivative of revenue, profit, or cost, this is called the marginal cost, the marginal revenue, or the marginal profit. So I'm going to go ahead and skip this problem really quick. Oh, I don't have it in here. It must be in the next section. I guess I'm not skipping this problem really quick. I'm gonna go through it. So what we want to do is we want to find the rate of change in the revenue for year 2001. So, excuse me, t equal to 0 is going to correspond to 2000. And revenue is going to be this function here. So we want to find the derivative. And we want to plug in t equal to 1, right? So what's the derivative of this? Well, r is equal to negative 110.194. I hate this book for all the decimals that it puts in. As we go through the semester, y'all are going to hear me say that almost every other class can guarantee that I hate these decimal problems. I would prefer that they write everything in fractions. Also, everything in the metric system. Like, it's the 21st century, guys. Just get with it. This is why we can't have nice things. Plus 23036 t is in the interval 0 to 5. So this funny e just means that t is in that interval. It's the same thing as saying same thing as that. All right, so t's in this interval. We want to take the derivative of this. Well, that's going to be the derivative of this. Plus the derivative of the second term. Plus the derivative of this third term. Plus the derivative of that last term. Well, this is going to end up being 3 times negative 110.194 t squared, right, by power rule. Here, this is going to end up being 2 times 999.98 t plus this term is going to have a derivative 1155.66, and this term has a derivative of 0. Holy shit, that sucked. Now we're just going to plug 1 in. That's it. So this is the function r prime with respect to t, right? So 1 is equal to 3 times negative 110.194. 1 squared is just 1. 2 times 999.98 times 1 plus 1155.66. I am not reducing it any further than that, because that's just straight arithmetic now, right? So what we're doing is finding the slope of the tangent line, the slope of the line tangent to our revenue function when time is equal to 1. That comes out to be about 2813, approximately. And that looks about right.
And so just checking,
Yeah, because that becomes 6. Yeah, that's about right. Yeah, what's up?
with, never mind, I think, yeah, I got it.
So, taking the derivative, they went ahead and actually evaluated out what it would be to multiply that 3 all the way through. Again, I wasn't going to do that because I'm not a human calculator. And then they evaluated what that revenue derivative would be at time equal to 1. So that is all of the first set of derivative stuff. The next bunch of things, we get over to those notes, week 5. Download them really quick. Right, so the next bunch of things will be things like the product rule. The product rule is going to be about the derivative of 2 functions multiplied together. So if you have a function f of x and a function g of x, and you multiply them, what's the derivative of that? So finding the derivative of this. But notice here, we could actually expand this out and find the derivative of the resulting polynomial. But if we have a way of finding the derivative of this and then finding the derivative of that, it saves us an extra step, right? Saves us the work of having to expand this out and then apply a derivative. That's kind of convenient. If we were to have more factors, shows the rule stays the same. We'll have the quotient rule, which is all about what happens when you have a function divided by another function and you take that derivative. Nice little mnemonic for y'all. And we're going to have things like the chain rule. The chain rule will be what happens when you have a function inside of another function. And with the chain rule, we'll be able to find things like the general power rule. We'll have all of our basic differentiation rules at that point. And then we're going to talk about rates of change. Instantaneous rates of change. And this is what I was talking about with marginal profit, marginal revenue, marginal cost. This is what I was actually looking for. So just since this last problem was already looking at marginal revenue, I thought we should go ahead and touch on it now. What marginal revenue and marginal cost and marginal profits are just the derivatives of your profit, revenue, or cost function with respect to demand. So let's say we have a profit function, and X is the number of units of an alarm clock that's being sold. If this is the profit function based on how they're sold, and we want to find the marginal profit at 50 units, we would just take the derivative of this thing, right? Now, let's say instead of profit, I gave you the revenue function. How would you find that?
Would that be,
Just the same thing, wouldn't it? Just another derivative. So what I'm asking is, how would you find the marginal revenue? It would just be the derivative. Does that make sense? What I'm asking? So I didn't mean to cut you off. I just realized like the way I asked that question was really weird. Like it really was a thicky way of asking it. What I was trying to ask is, instead of profit, if I had given you the revenue function and I asked you to find marginal revenue. There will eventually be problems that we'll be talking about that I want to kind of give you all a heads up on. So this is profit as a function of demand. Revenue is the number of products sold price. This is price as a function of demand. And revenue is the number of objects sold at that price point. So one of the things we'll be looking at is the interaction between price and revenues and how they relate to things like marginal revenue. Notice here we have a function times another function. That's going to be the product rule that I just alluded to. And that looks like the last of those notes. Yeah. Having said that, like I said, I just wanted to give you all a brief overview of what's going to happen next class. With 2 minutes left, y'all are free to go.